Okay, apologies for the delay. We're now ready to move on with the next presentation, which is by Akihiro Yatabe from NEC Corporation, who will be talking about ground state sampling and quantum annealing with the Sourlas-Lechner-Hauke-Zoller scheme.
Thank you for asking me. I'm Akihiro Yatabe from NEC Corporation. Sorry for inconvenient of these slides. The title is Ground State Sampling in Quantum Annealing with the Sourlas-Lechner-Hauke-Zoller scheme. This is the outline of this talk. First, I will explain the background knowledge and the motivation as an introduction. Then, I will introduce the numerical calculations and results, and you will get a general understanding. After that, I will evaluate the results using quantitative indicator to understand them more deeply. Finally, I will summarize this presentation and explain the future work. First, I explain the process of solving combinatorial optimization problem using quantum annealing. We start by formulating the problem as an Ising model. An Ising model is written as a quadratic expression, and the second order means the interaction. This formulated model is called a logical model in this presentation, and the variables are called logical. In general, any two variables interact with each other, so ideally, we would like to have a quantum annealing with fully connected graph where all variables are connected. However, the graph structure of the actual quantum annealing is not fully connected. Therefore, it is necessary to transform the logical model to match the graph structure of the quantum annealing. This transformation is called embedding, and the variables after transformation are called physical bits. After embedding, the embedded model is calculated using quantum annealing, and the calculation results is obtained as a value of the physical bit. Finally, the optimal solution of the logical model that you originally wanted to solve is obtained by transforming the solution of the physical bit. The quantum annealers made by UF Systems Inc. are well known, but NEC is also developing a quantum annealer. NEC's quantum annealer is based on Sourlas-Lechner-Hauke-Zoller scheme. The graph structure used in the SLD scheme consists of 4-bit unit cells. The same structure is implemented even if the number of qubits is increased, which has the advantage that the number of qubits can be easily increased. You may have heard of the LHD schemes. In this presentation, the LHD scheme and SLD scheme are the same. Initially, we thought that this scheme was first introduced by Lechner, Hauke, and Zoller, and therefore we call it the LHD scheme. But later, we found the same concept was developed earlier by Sourlas. So in this presentation, we respect Sourlas' work and call it this the SLD scheme. So let's take a closer look at SLD scheme. In the SLD scheme, the qubits are arranged in a triangle shape like this. The product of two logical bits is embedded to each physical qubits. As a result, the quadratic Ising model is converted into a linear expression. In addition, the number of bits increases from n to about n squared. As the number of bits increases, the number of possible states also increases, and solutions that cannot be decoded also appear. So it is a problem if a solution that cannot be decoded is obtained. Therefore, we add constraints called the fourbody interaction to prevent such solutions from occurring. The fourbody interaction is achieved by adding Hamiltonian such that the product of the four qubits connected by the range cross is 1. In byte solutions, the number of -1 is even. We will focus on the unfair sampling in this presentation. When there are multiple ground states, it is known that there is a bias in the probability of obtaining the ground state, and some ground states are more likely to appear than others. Let me explain this by an example of 3 ground states. Ideally, we would expect that each of the ground states appears equally, and all of the states A, B, and C are obtained. But in reality, some states are more likely to appear than others. For example, the state A is often obtained. However, we rarely get the state C. So we coordinate. So, wait. I think networking problem of this PC, so please wait. Yeah, sometimes. Okay, I understand.